devices to inform them to haul their you-know-what into class. I want you to stop me at exactly 1:25. We're going to spend about 5 minutes distributing the exams, and then you're going to be given half an hour to finish. Okay? Should I give you 2 minutes to text message your buddies, or can we proceed? At 1:25, I want you to stop me in my tracks. And that clock is pretty much correct. And then we'll spend about 5 minutes distributing the exams. There are way too many of you, so we can't do it instantaneously as much as we wish. And then you'll have half an hour to finish it. Okay. We were talking last time about periodic continuous time signals. I gave you a fairly straightforward example. I'm going to put up another example today. Let's look at this signal, cosine of t plus cosine of square root 2 of t, and tell find the number p such that if you shift the signal by that amount, you're going to get the same signal back. And the smallest positive p that you can find is the fundamental period. So go for it. Figure out if this signal is periodic. If so, what is its fundamental period? If it's not periodic, then you need to explain why it isn't. Who needs more time? Okay, not to move. Okay, you have 40 more seconds. when that wire is in. All right, Meatball, where are you? Okay, today you need to pick somebody else because then we're going to have otherwise we have a game theoretic problem where on the first example every lecture they're going to think you're going to do it and they're not going to pay attention. So pick somebody. Well, we got Euro. You are? Jason. Go for it, Jason. What have you got?
Well, say x of t plus b.
Give us the upshot that you're trying. Give us the goal you're trying to get to. Is it periodic or not, according to
Well, it satisfies that equation of top left.
Okay, and does it based on what you just did in the last few minutes?
Well, I didn't actually finish it.
Okay, so x of t plus p, Jason says. Let's do it. What do you have on the right hand side?
Cosine of t plus cosine of root 2 and 1.
Okay. Pass the buck. Tim. Well, what does p have to be for this term to give you back cosine? 2 what? 2 pi or some integer multiple. And what about for the second term? So here you've got cosine square root of 2t plus square root of 2p. What's zero? You're adding something to the original angle. The original argument was square root of 2t. You're adding something to it. So root 2 pi must be, again, there's that integer ambiguity. What this says is that p must be 2 pi over square root of 2 times L. This says p must be some integer multiple of 2 pi. Can you satisfy both of these equations simultaneously? Why not? And get what? Okay, let's do that. So, in the first equation, you're saying substitute for L. So L is equal to what? P over 2 pi. Who objects to this step? Well, that's actually a degree of freedom. You can play around with that. You can choose k to be one integer, L to be another integer. But what's wrong with this step? What's wrong with saying L is equal to P over 2 pi? It's not an integer. It doesn't necessarily guarantee that L is an integer. Not necessarily an integer. Oh, I made a mistake. Let's see. This is k. So this is k. Okay, so you're saying, let's equate the p's. Cancel out 2 pi. So k over L, which is what kind of a number? A rational number, is equal to 1 over square root of 2, which can't happen. Now, there's something I've been sweeping under the rug, which is that I have a summation of two signals, and I'm sort of claiming that for the summation to be periodic, each of the components, the P that you find has to satisfy periodicity of each of the components. That's not a trivial claim, because you can have two components adding together and just canceling out in just the right way, potentially, so that the sum is periodic for a particular P, but each of the components is not. And there's a problem set problem that you'll go through where you deal with this particular nuance. But right now the main point is you can't have k and L be integers and one be an irrational multiple of the other. No integer is an irrational multiple of another integer. So this signal is not periodic. What about this signal? Is it periodic? And if so, can you find the fundamental period? The second question is far more important than the first. So what's the verdict? Is it periodic?
Yes.
It is periodic because you can definitely find a number p such that if you shift this signal, you get the same signal back. Does it have a fundamental period?
No.
Why not?
For any real number greater than 0, there is just a real number less than that real number that's also greater than 0.
Exactly. There is no smallest positive number that works. Any number you give me, as small as it may be, I can find a smaller positive number for which this relationship holds. So this is periodic, but has no fundamental period. And this is where we have to appeal to our understanding, our intuitive understanding of what it means, what frequency means, to determine whether, or to determine what the frequency content of the signal is. What is the frequency content of the signal? 0. This signal has only one frequency, and it's at 0. So if I were to draw its spectrum, it would be that infamous arrow, which I haven't defined for you yet, and it's at 0. And it's got some kind of a strength alpha, which I will describe later. But the point is, it has no frequency content, anywhere other than 0. This is a DC signal. The quintessential DC signal that you've seen in your physics courses. And if you've taken EE40, also in EE40. So this signal has no variation. Intuitively, the more the signal varies in time, the higher the frequency content. The smoother it is, the lower the frequency content, the tighter the spectrum. You can't get smoother than this. This is a constant signal. And there is no oscillation, no variation, no variability. And so the only frequency that's present in the signal is at 0. We'll say a lot more about this later. Okay, let's move to discrete time. A discrete time signal is called periodic if the same kind of relationship holds for all n, but in this case, p has to be an integer. It can't be an arbitrary number. And the reason is that when you look at a discrete time signal, let's say this one, say this is 1, 1/2, -2, whatever. This is your x of n. What is x of 1/2? Huh? It's undefined. And you'd be amazed how many students write expressions like these for discrete time signal. Remember, the domain of a discrete time signal is the set of integers. This is not an integer. And on this side, you can have real, you can have complex, you can have any number of things. But the point is, the domain of a discrete time signal is a set of integers, or some subset of the integers. And so, to talk about x of 1/2, conversation. And that's why when we describe periodicity, we can't talk about non-integer shifts of the signal. You can only shift a discrete time signal by an integer number of samples to the right or to the left. And it's this restriction on p that creates some nuances that exist for discrete time signals that don't exist in continuous time signals. Let's take a look. So x of n equals 5. Periodic? Yes or no? Yes. What's the period? Period is 1. The fundamental period. I'll just say period is 1. See, we don't run into that problem for discrete time. Because here, the minimum positive number is clear. You shift the signal to the right or to the left by 1, and you get the same signal back. So the minimum shift is the fundamental period. The fundamental frequency is defined as 2 pi over p. Same as in the continuous time story. I didn't write, yeah. See, to answer, I asked 2 questions with regards to this signal. My first question was, is it periodic? To answer that question, all you need to find is 1p, for which this holds for all values of t. Okay? Well, that's the problem. That's why I said, in this case, you can't use the relationship between the period and the frequency to arrive at this expression. You have to appeal to what your intuition says about frequency. Frequency relates to oscillations or variations in a signal. The more discontinuous a signal or the faster it varies, the footprint in the along the frequency axis will be wider. The smoother and the less variable it is, the footprint will be narrower. This is the narrowest, this gives you the narrowest footprint possible because it has no variability whatsoever. It's constant throughout all time. So it can't have anything other than zero frequency. We will derive this mathematically later when we talk about Fourier transforms. But the point is you don't have to wait that long to understand the relationship between this signal and its spectrum. So here, what's the fundamental frequency then? 2 pi. What are the units? Radians?
Per sample.
For what?
Per sample.
Where is second in all this? Per? I heard it. Sample. In discrete time, you have samples. It's not necessarily the case that I got this signal from by sampling a continuous time signal. This is a discrete time signal. It stands on its own feet. You don't know what this n came from, or if it came from anything at all. All you know is that these values are samples. Each of these integers is called a sample. So x at 1 is x evaluated at sample 1. X at minus 1 is x evaluated at sample minus 1. So frequency in discrete time has the units radians per sample. Its counterpart to hertz, F naught, which is omega naught over 2 pi, will have units of what? One of you guys said it. In answer to the previous question, you used the C word. Huh? Samples per second? One oscillation is what? One cycle. So it's cycles per sample. This very often is not used. Actually, some books use the letter phi naught. But we rarely deal with this unit of frequency in discrete time. Okay. Here's another thing. Comparing continuous time with discrete time. In continuous time, you had a fundamental period, and you had a fundamental frequency, which was 2 pi over p. And as long as p was not equal to 0, you could say as long as omega naught was not equal to 0, you could say p is equal to 2 pi over omega naught. No problem. So in discrete time, you have the period p, period. And you have omega naught, fundamental frequency. No problem. What is the problem with writing p is equal to 2 pi over omega naught? Even if omega naught is not 0. Huh? You might not get an integer. So don't use. Because it's not necessarily an integer. So there are these subtleties that you have to deal with when hopping back and forth between continuous time and discrete time. There aren't too many of these. I mean, we've pretty much covered them. Now let's do some examples. Let's say x of n is cosine pi over 4n. Tell me if it's periodic. Talk to your neighbors. Tell me if it's periodic. And if so, what its fundamental frequency is and fundamental period. This is a softball. Okay. Who was my last victim? Jason? Pick somebody. 2 rows back. That's you. Next to Reggie. You are? Whitney? No, I do mind. Well, you need to walk us through it. How do you get it? Imagine they all have donkey ears on their heads. So you're looking at x of n plus p. And that's cosine pi over 4n plus pi over 4 p. Okay? Now what can you tell me about pi over 4 p? Pi over 4 p must be equal to not just 2 pi. 2 pi k, some integer. You've got to build in that flexibility because it's not necessarily the case that 2 pi is going to do the trick for you. Okay, now what? So p is equal to what? So what happens to the pi's? I cancel the pi's. And then p is going to be equal to what? 8k. Now, what's the smallest p that you can give me? For what value of k? 1. So smallest p comes from k equals 1. So in this case, if you had just put k, if you hadn't put k, it would have worked. But it's not always going to work. So the period is 8. And the fundamental frequency is? It's already in the cosine. 2 pi over 8, which is the same as pi over 4. Okay. Now let's do another one. xn equals cosine pi over 2n. This has got to go more quickly. Okay, now you get to pick somebody else. I can't hear you. Just make eye contact with whomever you want to pick. End of this row. I have astigmatic. I can't follow the... You are? Gene. Eugene or Gene? Eugene. Okay, Eugene. What have you got? X of n plus p. P. So pi over 2p must be what? 2 pi k. And what does that give you for p? P is equal to 4k. The pi's again cancel out, so you get 4k. And smallest k is? Use k equals 1, so p is 4. And your fundamental frequency is? You usually grab it from there, but if you want to verify, it's going to be 2 pi over p. 2 pi over 4, which is pi over 2.
Are we allowed to use that formula, the 2 pi over 1 in each section?
If it's an integer, it's not guaranteed to give you the smallest integer. That's the problem. And that actually touches on an important distinction between continuous time signals and discrete time signals. In continuous time, as you increase the frequency monotonically, the period decreases monotonically because they have an inverse relationship. That's not the case in discrete time. And you'll see. I mean, the reason I'm going, notice I'm going from pi over 4 to pi over 2. Next example is going to be 3 pi over 4. Actually, you should already be able to see this. Yeah, you can already see it. Going from the constant signal, what was the period? Frequency was 0, period was 1. When I went from here to here, I increased the frequency, but the period didn't go down. So that monotonically inverse relationship between the frequency and the period that you see in continuous time doesn't exist here. You go from the slowest varying signal, which is the constant, its period is 1. You go to pi over 4, its frequency is higher, you'd expect the period to be shorter, but it's not. And then you go, now here, there's a region where it starts decreasing. So you go to a higher frequency, period decreases. But then again, it starts increasing. So when you go from here to, I'll let you sort out x of n equals cosine 3 pi over 4n and see what you get. But then the next case is more interesting, which is x of n equals cosine pi n. Can you simplify cosine pi n?
Yeah.
How?
Negative 1.
Plot this. Plot cosine pi n. What do you get? When n is 0, 1. When n is 1, negative 1. When n is 2, 1. When n is minus 1, negative 1. So it's the same as minus 1 to the n. There's an exponential form of this also. E to the I pi n. In different contexts, you may want to use one of these different forms to make your manipulations easier. E to the I pi n, we're claiming is equal to cosine pi n. Does that make sense? This is the real part of that. So how does it make sense? Sine pi n is always 0. So the imaginary part of this is always 0. Okay, so this is 1, 0, 1, minus 1. And it oscillates between 1 and minus 1. This, ladies and gentlemen, is the fastest discrete time signal in existence. Fastest varying signal. It has the highest frequency possible. The highest frequency for discrete time is pi. The highest frequency for discrete time signals is pi. There is no signal that varies faster than this. This oscillates, it changes polarity from sample to sample. But even this doesn't have the shortest period. What's the period? 2. So it's good to look at the unit circle and see what we're doing. When you look at a signal of the form e to the I omega naught n, you're essentially tied to going around the unit circle and coming back to where you were. This is the real axis. This is the imaginary axis. So we started with 0 frequency. That's around here, the angle that it makes. This is 0 frequency. Omega naught equals 0. This is omega naught equals pi. Everything else was in between. So this was omega naught equals pi over 4. Omega naught equals pi over 2. And in general, frequencies around 0, these frequencies around 0, are considered low frequencies. And frequencies around pi are considered high frequencies. And everything else is mid-range. Notice what happens when I go from e to the I 0n, which is what? The signal 1. I add 2 pi to the frequency. What do I get? 1. In fact, e to the I 2 pi k n, all integer multiples of 2 pi, land you at this location on the unit circle, and they all correspond to the same frequency. This feature does not exist for continuous time. It exists for discrete time because when you look at e to the I omega naught n, e to the I omega naught plus 2 pi n. If I add 2 pi to my frequency, what do I get? I get e to the I omega naught n times e to the I 2 pi n. And this is always 1. So I get back a signal in the first rotation on the unit circle. And this works because n is an integer. In continuous time, you have e to the I omega naught plus 2 pi times t. And so the second factor will be e to the I 2 pi times t. T is a continuous variable, and therefore e to the I 2 pi t is not guaranteed to be 1. But in discrete time, this is always guaranteed to be 1 because n is an integer. So you add any integer multiple of 2 pi here, and you'll have the same thing here, and it still will be 1. And so there's no distinction between the frequencies 0, 2 pi, minus 2 pi, 4 pi, minus 6 pi, and so on. And the same is true for all of these. So all odd multiples of pi correspond to the highest frequency. Pi, minus pi, 3 pi, 5 pi, they all land in the same place. The frequency omega naught equals pi over 4 is the same as omega naught, is the same as pi over 4 plus 2 pi, 9 pi over 4, and so on. So in discrete time, your frequency space is limited to essentially 0 to pi and 0 to minus pi. Around one circle. Okay? I need to... Was there another point I wanted to make before? We'll break. We'll continue next time. Okay. TAs. Where are you? Please put away everything. The quiz is not open book, open notes. Don't forget I have office hours tonight, 6 to 8. And remember that for the first midterm, you are allowed 1 page of your own handwritten notes with no appendage. That means you don't put those flip-flop pieces of paper. Just on 1 page, both sides of notes. For the second midterm, you'll have 2. For the third midterm, you'll have 3. But for the first one, you have only 1.